Turán numbers of cycles in 3 uniform linear hypergraphs.
Hello. First of all, I'd like to thank organizers for inviting me to speak here. My talk is going to be about Turán numbers of cycles in 3 uniform hypergraphs. And in case hypergraphs is not your cup of tea, don't worry, because linear hypergraphs act mostly like graphs. And if graphs isn't your cup of tea, then there's always internet. You can scroll Facebook. So let's start with basic definitions. A linear hypergraph is a hypergraph where every two hyperedge intersect at most in one vertex. And let's define the Beer cycle. Beer cycle is alternating sequence of distinct vertices and hyperedges, and each hyperedge hi contains neighboring vertices vi minus 1, vi and vi plus 1, and there are no extra requirements. And linear cycle is a Beer cycle, but we put the extra requirement that only neighboring hyperedges, cyclically consecutive hyperedges, can intersect, and they intersect exactly in one vertex. So also these vertices v1, v2, and vk, sometimes I might refer to it as base vertices of the cycle, and or sometimes base cycle. So here are just drawing examples of 3 uniform linear C5, and here is Beer's C7 in a linear hypergraph. So even when the hypergraph is linear, Beer's is still not same as linear. Now let's define linear Turán number. So linear Turán number is if you have a family of forbidden hypergraphs, then we denote it as by x, 3 lin, and f, which is we cannot have any hypergraph of f in the hypergraph, and we have to maximize number of edges. So for formality here, sometimes when we have not family, just one particular hypergraph forbidden, then we just write f instead of set of f. So let's talk a little bit about history before we go into the main theorems of the talk. So this talk is about forbidding Beer cycles in the linear hypergraph. So let's start with smallest cycle, C3. And this problem is actually equivalent of the famous 6-3 problem by Erdős, Brown, and Schaus. And it was determined by Ruja and Semeredi, and it's little of n squared. So next is C4. We do not have theorem for just linear Turán number of Beer C4, but we had by Lazebnik and Westrate a linear Turán number of C3 and C4, which has asymptotically sharp bound, which is 1/6 n to the 3/2. And we showed, together with Erwin Jury and Abhishek Metuku, we showed that the requirement of C3 is not necessary, so the extremal number is still the same, asymptotically. Actually, everything in this talk is asymptotically, so sometimes I might forget it, but when I say sharp, it's asymptotically sharp. So the theorem is that extremal number of C4 in linear number of C4 is same as forbidding C3 and C4. Of course, construction is the same. Now C5. So
you mean the error is little o over 3/2, not big O n?
Sorry?
So the error in just C4 is little o n to the 3/2, not big O n. So you mean, oh, there's twiddle.
Here?
Yeah. So there's a twiddle between the first two things.
Oh, both of them are big.
The question is, do you...
The second bit.
This?
Second bit. No, but there's a twiddle.
That twiddle, yeah. That twiddle means one to low 1.
I think little of n.
It's still big O n.
Big of n, so why did I say little? So it's the same.
It's
So,
the same, okay.
okay. Yeah, so I might be very not careful about asymptotics, which, sorry, I apologize for that. So our main theorem, which we proved, is linear Turán number of C5, which order of magnitude was, even order of magnitude was unknown. At least for us, it was unknown. So I don't know, I did not fact check completely. but asymptotics at least for sure was unknown. And we found that we thought that it was little of n to the 3/2, but it turned out that we found the construction of n to the 3/2, and we proved this sharp bound. And I also want to talk about this just forbidding Beer C5 in not linear hypergraphs, but all the hypergraphs. And that was a problem solved by Bolobash and Jury, which has the same lower bound as the linear case, but their construction is not very linear, and this construction is completely different, but it has same number of edges. And I want to say also that this construction does not even have C3s, so triangles. And upper bound was √2. So when we solved this theorem, we thought that, OK, let's apply this theorem somehow, and let's improve their bound. And we quickly improved it by some modifications. But we did not write up because we thought that we would improve further. But time had passed, and now not only we don't remember how we proved it, we don't even remember what bound we got. But I promise that in future we'll go back to it and write up. So this is a construction. I got a little bit carried away by colors, but you know, it's easy to get attention by shiny things. So this is a construction of Beer C5 free linear hypergraph. So the way we construct it is just we take √n/3 size set L1 and √n/3 size set L2, R1. And we take complete bipartite graph in between. And we, for each edge in this bipartite graph, we create a new vertex in B. And so there's a bijection between these edges and vertices here, and we put a hyperedge there. And what we do is just we take this hypergraph, and we make many copies of this and identify vertices of B. So if you didn't understand what I said, I think it's still kind of clear from the picture that so this yellow vertex is connected to only these yellow edges, so similar edges in the bipartite graph. Red is connected to red, and so on. So now let's check that it doesn't have C5. So if it has a C5, where is the base cycle of this C5? So base cycle cannot be here, because it has to use one vertex from B at least, because of its the upper. This is bipartite. Let's say it uses one vertex of B, like this. Then it's easy to see that it's impossible, because this vertex, for example, this yellow vertex, has only one hyperedge connecting to this set. So, but there are two edges of base cycle, so we need two hyperedges containing these edges of base cycle. So it's impossible that C5 is like this. And let's say it contains two vertices from B. This vertices of B has interesting property that every pair either has two paths between them or three paths. It's impossible to have both of them. For example, here, if you take this yellow one and the green one, there is a cherry here. And if you want to find the three paths here, it's easy to see after a while that we have to use one edge twice. For example, we go by yellow edge. So we go here by green edge, but the connecting bridge edge has to be yellow again, which is not allowed. So let's prove the upper bound now. So as I said, this is also C3 free. I did not show it, but it is anyway. So here we assume, for simplicity of showing the ideas of proofs, we just assume that it's C3 free also, and then we prove upper bound for weaker problem. So proving without C3 freeness, it gets longer and uglier. But for simplicity, let's prove much simpler problem for now. But the main ideas are mostly the same. So let D be average degree of a hypergraph. So we are going to use everything upper bound average degree. So this is important to memorize that D is average degree of a hypergraph. And we just have to prove that D is upper bounded by √n/3. So we are going to use the classical trick that if we have a vertex of less than D/3, if we delete this vertex, in the remaining hypergraph, average degree will not decrease. So whatever the bound we will get in the remaining hypergraph, we will get for original hypergraph. So we can make this assumption that minimum degree is bounded by D/3. So this is a proof of sketch. We will prove that maximum degree is at most 60. This 6 doesn't matter asymptotically, actually, constant times D. Next, we'll lower bound the number. So Why 3 walks? So the main proof relies on the fact counting 3 paths, lower bounding 3 paths in hypergraph. So for that, first we observe shadow graph. We lower bound number of 3 paths there, and then we lower bound number of hyper-edge 3 paths in the hypergraph. So first we lower bound actual number of 3 walks, and then we prove that there is a hyper-edge edge, which then we prove that there are many 3 paths in hypergraph, and then we prove that there is it implies that there is a one hyper-edge from where the many 3 paths start. Start, finish is it's the same, so symmetrical. And then we combining these things and upper bound. So before we follow this sketch of proof, I want to say one lemma, which is very important lemma for this proof. If we start from a vertex V and we consider all the 2 paths starting from V, so this N is first neighborhood of V, S is second neighborhood of V. So this has this nice structure because there is no hyperedge like this because we assume triangle freeness. So in original problem we had, and we had to get rid of them. But for simplicity, we don't have now. And we proved that size of S is at least as big as number of hyperedges, number of 2 paths starting from V, which is actually same as number of hyperedges here, which is essentially the same as the number of edges in the shadow created by these green hyperedges. And the way we proved, actually, I'm not going to go into details, but we proved that in the shadow, in S, we don't have this shape. We don't have a triangle, and we don't have a big cycle and this big, I mean 4 and more. So we get that it's union of stars and cycles, so shadow graph with these green edges. So we get that S is as big as number of 2 paths starting from V. And with this trick, and by assumption that minimum degree is d over 3, we can bound maximum degree, which also I'm not going to go into the details here. So now, lower bounding number of 3 paths. We start with lower bounding number of 3 walks. Black-Leroy inequality is a matrix version of Hölder's inequality. And it implies that graph with average degree dg has at least this many number of walks. So linearity of h implies that degree of each vertex in the shadow is twice the degree of in h. And then we put 2d here, and we get the bound that we have 4 nd cube unordered walk length of 3. But we wanted to upper bound number of 3 paths in hypergraph. And so these 3 paths, oh, this is not very visible. So these 3 paths in hypergraph, we want to bound the number of 3 walks which kind of correspond to 3 paths in hypergraph. As you see here, these 4 different 3 paths which are in the shadow, 3 walks, if you want, corresponding to 1 3 paths in hypergraph. So these kind of 3 paths which live inside 3 paths of hypergraph, we call it good 3 walks on good 3 paths. And bad 3 walks are these walks which have nothing to do with hypergraph 3 walks. And because of the upper bounded maximum degree, it's easy to see that, for example, these are not even paths. This is a path, but it does not live in 3 hypergraph paths. But it's easy to see that everything is upper bounded by constant times square of degree of V. And because of max degree is bounded by constant times average degree, then it's negligible. So we get rid of bad walks, and we know that we have 4 NDQ plus big O of D square good 3 paths. And if we divide it by 4, we will get lower bound of how many hypergraph paths we have. So I already said this. So so we have this many paths, and each path has 2 and hyper edges. So and there are number of edges is n times d over 3. So if you do the calculation, we will get that there is a hyper edge h from where 6d square 3 paths start. So let's take this hyper edge h, and we know that many 3 paths start from here. Let's say it's A, B, and C, and we define let PA be number of, so all the 3 walks has to go either through A, either through B, either through C. So we drew this. These are separate drawings, and there might be vertex repetitions and even hypergraph repetitions. So this is separate from this. But let PA be number of 3 paths which go through A. So it's basically the same number of 2 paths starting from A. Let's look at SA, SB, and SC are second neighborhood of A, second neighborhood of B, second neighborhood of C. And if we apply the lemma we discussed before, the number of 2 paths starting from A is upper bounded by number of vertices here. So SA is at least number of 3 paths here, SB is number of 3 paths here, SC is at least number of 3 paths here. Also, we show that there cannot be a vertex U, can be here, and it can be here also, but then it cannot be on the SC. So it's just easy if you draw, and if you see that one vertex is in 3 of the drawings, then you can easily find C5. So it's impossible that one vertex can be in all of the drawings. So by this, we get the upper bound of, so sum of this is at most 2 times the union of this. Yeah, by lemma this. So clearly, number of 3 paths starting, which start from H, such that H is a terminal edge, so first or last, is PA plus PB plus PC, because it's either drawn here or here. Clearly, so we can write the inequality now. This is number of edges, so 3 paths starting from H. This is less than PA plus PB plus PC. And by lemma, it's less than SA, second neighborhood of A, second neighborhood of B, second neighborhood of C, and it's less than union of SA union SB union SC, which is less than 2n because it's subset of all the vertices. So we get the desired bound from this. So proof with this mainly uses the same ideas if you allow C3 to be there, but there are like a lot of technical issues. But this is main tools. So before finishing the talk, I want to discuss some different problem, which is not different actually. These problems are derived by generalized construction of the previous construction, which I'm going to talk about in a bit. So theorem of Collier-Cartiano, Graber, and Jiang. It was that if L is more than 3, we forbid linear cycles instead of burst cycles. And if we forbid linear L cycle, they prove that upper bound is order of magnitude of n to the 1 plus 1 L over 2 floor. So what we did, we decided to match this bound, but for odd cycles, because our construction was for odd cycle, working for odd cycles. We have a theorem that if k is equal to 2, 3, 4, and 6, we match this lower bound asymptotically. But here, okay, L is different and k is different. So L will be 2k plus 1, and if you substitute, you will get the same exponent to what is there. And actually, we proved a more general theorem, but we could not get sharp bound for other k's because of we used, okay, sorry, one thing I had to mention. This C is script C, which means that it's forbidden not only linear cycle of C2k plus 1, but all the odd cycles less than C2k plus 1. So the construction does not have any odd cycles less than C2k plus 1. And here is only one odd cycle forbidden. And actually, we proved a much stronger theorem, not stronger, general theorem, that if we have a bipartite extremal number of this C2k minus 2, which is all the even cycles before 2k minus 2, so basically girth is C2k plus 1. So then if we have this bound into the alpha for some, okay, I don't use C, I copied this, and we had general, more detailed bound depending on C. But anyway, if we have this, then extremal number is this. So conjecture, I forgot whose conjecture. Abhishek, you would know. Okay, you are not listening. Never. Boundish image, yeah. Sorry. Conjecture is that this number is n to the 1 plus 1 over k. And so if the conjecture is true, the lower bound of this extremal number is true, then when we insert it in our theorem, everything gets sharp here for even cycles. So every time they improve this bipartite lower bound by I don't know why I say that, maybe we improve it, but we get better construction and we get sharp construction for here. So if the conjecture of them is true, then we have sharp result for every 2K1 cycle here. Sorry?
What is this conjecture?
That's this extremal number of these. So forbidding, so Gertz C2K plus 1 has order of magnitude n to the 1 plus 1 over k minus 1, but
No, so I think Beka is talking about the general graph question.
graph question, yeah.
So if you have a graph of more than 2k, then the extremal number is infinite. So there are no constructions, but there are
Everything's model.
yeah. So Erdős is conjecture and condition is provided. That's what happens.
So that's the conjecture.
Oh, okay. He is the responsible for the conjectures and theorems. I'm just responsible for only proofs. And so how did we construct this generalized construction? So I put the same drawing. I got a little bit lazy as previous construction, but remember how we constructed this? We just put the complete bipartite graph here. We created vertices and we constructed. Now instead of complete bipartite graph, we put this bipartite graph. So bipartite graph which does not have C2K minus 2, C2K minus 4, and all this cycle. And if we put that graph here and we construct the similar example, it will provide the example which does not have any odd cycles up to C2K plus 1. Yeah, so now open problems. So first, a natural open problem, and the open problem which I really like, but I could not get my co-authors excited, very much excited, and I was too lazy to think about it alone. So if you want to think about it, I will happily betray them. Linear Turán number of C5 we already discussed. We have sharp asymptotics. Linear number of C4 we also have sharp asymptotics. And what about if we restrict both of them? And what is the order of magnitude? We don't know what is the order of magnitude of this. So I think it's a very nice question. And next question is about do the same thing but forbidding. So whatever we did here for odd cycles to do the same for even cycles here, and we don't know again the order of magnitude, and we don't have good constructions for it. So these are two of my favorite open problems about it. Thank you.